Hi, everybody, and welcome to our first video lecture of spring 2024, Calculus 2. I'm not able to be in the classroom for a few days, so we're going to do some video lectures instead. And hopefully these will be very good. Study them carefully and take notes just like you were in class, okay? What we're going to look at today are the properties of definite integrals, and we will assume that f of x and g of x are continuous functions. By this time, we have done some area problems using Riemann sums, and we've done some area problems using the f minus g method. So a lot of this is not going to shock us, but it's going to be stuff that we kind of already know. But we want to formalize things and write down 7 properties of definite integrals that we need to remember. And the first one is that if we have a definite integral of a constant times a function, that's the same thing as the constant times the definite integral of the function. So in other words, if we have a definite integral, constant times a function, we can just take that constant factor and just slide it out in front of the integral sign. The second property of definite integrals is that the definite integral of a sum or difference of functions is the sum or difference of the definite integrals of the functions. So if we have to, we can integrate each term separately and then just add the results. The third property, this looks kind of stupid, but I'm going to mention it anyway because I think it might come in handy if we just acknowledge it right now. This is not a mistake. I have deliberately made the bottom limit of the integral and the upper limit of the integral one and the same thing. The lower limit is a, the upper limit is a. And when we compute the definite integral of a function from a to a, we get 0. By the way, I am going to look at each one of these properties and justify them. These two I'll give a very brief justification of. The other properties I will give a little bit more in-depth justification of. But if the lower limit and the upper limit of the integral are the same, and f of x is a continuous function, this thing's just going to be 0. I know, you're all shocked, right? Well, it's one of those things that I have a feeling it may just be helpful for us to acknowledge this ahead of time. Here, property number 4, that we have the integral from a to c of f of x and the integral from c to b of f of x. And notice that the upper limit of the first integral is the same as the lower limit of the second integral. The upper limit of the first integral, c, is the same as the lower limit of the second integral. And what happens here? We end up getting an integral that has as its lower limit the lower limit of the first integral, and as its upper limit, the upper limit of the second integral. So it's almost as if we cut the top part of this integral off and the bottom part of this integral off, and we put the top part of this integral over here. But if the upper limit of the first is the same as the lower limit of the second, then we get the integral from the lower limit of the first to the upper limit of the second. That's what that turns out to be. And we'll give a geometric proof to that and also an algebraic proof. Once we see this, it'll make quite a bit of sense, especially if we look at it geometrically. The fifth property, did you ever wonder what would happen if we took the integral from a to b of f of x and switched the upper and lower limits? We took the upper limit, put it down here, and we took the lower limit, put it up here. Well, the resulting integral would be the negative of the original integral. If we take an integral from a to b f of x and we switch the upper and lower limits, the result is going to be the negative of the original integral. So if we switch the upper and lower limits, it changes the sign of the answer, plus or minus. Doesn't change the magnitude of the answer, but it changes the sign, plus or minus, of the answer. Property number 6. If f of x is non-negative, in other words, the graph lies completely above the x-axis, then the integral from a to b of f of x is equal to the area bounded by the graph of f of x and the x-axis between x equal a and x equal b. And by the way, this may be too small for you to read, but this says y equals f of x. That's what that graph is. So if f of x is non-negative, the graph lies above the x-axis, and the integral from a to b of f of x is the area between the graph of f of x and the x-axis between x equal a and x equal b. And our last property, suppose f of x is non-positive, in other words, less than or equal to 0. In this case, the graph of f of x, and here it is right here, lies completely below the x-axis. Well, in this case, if we take the area between the graph of f of x and the x-axis, the integral from a to b of f of x is going to be the negative of that area. So if the graph of f of x lies below the x-axis and a is less than b, the integral is going to be the negative of the area bounded by the graph of f of x and the x-axis. Now let's take a quick look at each of these properties separately. Okay, property number 1. The definite integral of a constant times a function equals the constant times the definite integral of the function. And this essentially is because the antiderivative of a constant times a function is equal to the constant times the antiderivative. And let's just show this. If we're computing the definite integral, what do? First thing we do is we compute the antiderivative of this thing. The antiderivative of c times little f of x dx, and we evaluate it from x equal a to x equal b. But we know because of the properties of antiderivatives that we can move this constant out in front of the integral sign. So this becomes c times the antiderivative of f of x dx. That's a horrible integral sign. There, that's even worse. Oh well. This is the constant times the antiderivative of f of x dx from x equal a to x equal b. And that's equal to c f of x, where f of x is the antiderivative of little f of x, any antiderivative of little f of x, evaluated at x equal a to x equal b. Okay. Now, let's try the same thing with this. What do we get if we have c, definite integral from a to b, of little f of x dx? Well, that's going to equal c times the antiderivative of f of x, which is big F of x, evaluated from x equal a and x equal b. And let's see what I have here. I'm going to get c times f of b minus f of a. Okay. And that's going to be c f of b. I can just take the constant and distribute it inside the parentheses times c f of a. Well, let's see. What would I get if I actually evaluated this? I'd get the antiderivative c f of x at the upper limit, which would be c f of b, and then I'd subtract the antiderivative evaluated at the lower limit, c f evaluated at a. So I'd get c f of b minus c f of a, which is exactly this thing. Okay. So I think I have a chain of equalities here. If I start here, this is equal to that, which is equal to that, which is equal to that, which is equal to this, which is equal to this, which is equal to this, which is equal to this. That is, the definite integral of a constant times a function equals the constant times the definite integral of the function. Now, this is probably a much too detailed explanation for why this works. The bottom line is this. We have the property that for antiderivatives, the antiderivative of a constant times a function equals the constant times the antiderivative of the function. And that's exactly why this works for definite integrals. Because when we compute a definite integral, we compute the antiderivative and plug in the upper and lower limits. Instead of over-explaining the obvious like I did the first one, I think I'm going to cut to the chase on this one. What we're claiming is that the definite integral of the sum or difference of functions is going to be the sum or difference of the two definite integrals. In other words, we can compute the definite integral of a sum or difference term by term. And this is just a direct consequence of the fact that the antiderivative of the sum or difference of terms is the sum or difference of the two antiderivatives. In other words, if we have the antiderivative of a sum or difference, we just compute the antiderivative term by term. Compute the antiderivative of this term, compute the antiderivative of that term, and so forth, and just add them all up when we're done. Okay, this one we'll do two ways. We'll look at it algebraically and numerically, and then we'll look at it geometrically. The key here is to recognize that the lower limit of the integral and the upper limit of the integral are one and the same thing. So let's just evaluate this and see what we get. The integral from x equal a to x equal a of little f of x dx. What do? We compute the antiderivative, capital F, and since any antiderivative will do, but we very conveniently choose the antiderivative that has a constant term of 0. And we're going to evaluate this from the lower limit, x equal a, to the upper limit, x equal a. First thing we do, we plug in the upper limit, and then we plug in the lower limit, and we subtract one from the other. Capital F of a minus capital F of a is 0. That's why it works numerically or algebraically. Let's go back and let's look at this same thing geometrically, okay? Now, let's just suppose that f of x is non-negative, okay? F of x is non-negative, so its graph lies above the x-axis. In that case, geometrically, what is this? If f of x is non-negative, the definite integral, here's y equals f of x. Isn't this definite integral the area bounded between the graph of f of x and the x-axis between x equal a and x equal a? The area between the graph of f of x and the x-axis from the lower limit to the upper limit on the x-axis. And the upper and lower limits are the same. What is this? Here's our answer. It's the area bounded by the graph of f of x and the x-axis between x equal a and x equal a. So this region has the width of one point. What's the width of a point? Isn't it 0? So essentially, we're looking at a rectangle whose height is whose height is little f of a. That's the height, and its width is the width of a point, which is 0. The area bounded by the graph of f of x and the x-axis between x equal a and x equal a is the width of that, is the area of this rectangle. A rectangle which has height f of a and width 0. Well, let's see, the area is height times width, and the width is 0. Son of a gun. the area of that region equals 0. Okay, now I get it. Next property. Next property of definite integrals. The integral from a to c of f of x plus the integral from c to b of f of x is equal to the integral from the lower limit of the first to the upper limit of the second. And notice here, the upper limit of the first and the lower limit of the second are the same. Notice also that the function is the same. In each case, we're integrating f of x. And what do we get? Well, we get one integral. We cut out the middleman c, and we integrate from a to b. We're going to see why this works algebraically or numerically first. And then we're going to look at an algebraic justification of it that I think is going to make a lot of sense. Let's look at it numerically and algebraically first. The integral from a to c, little f of x dx, plus the integral from c to b, little f of x dx. And what do we get with this one? We get the antiderivative of little f, which is capital F. And we'll choose the antiderivative that has a constant term of 0. We're going to we're going to evaluate this antiderivative from x equal a to x equals c. And we're going to do the same kind of thing here. We're going to compute the antiderivative of little f, and we'll get capital F. And we're going to have as the upper limit b, as the lower limit c. Now, let's evaluate each of these things. Here we're going to get capital F evaluated at the upper limit minus capital F evaluated at the lower limit plus capital F evaluated at the upper limit, looking good, minus capital F evaluated at the lower limit. And notice something. We have capital F evaluated at C minus capital F evaluated at C. Those two add up to 0. And what do we have left? Negative f of a plus positive f of b. And I'll just reverse the order. F of b minus capital F of a. And isn't this the integral from a to b of little f of x dx? The integral of little f of x dx, we take the antiderivative, capital F evaluated at b, capital F of b, evaluated at a, capital F of a, subtract 1 from the other. Okay. So we started out with the antiderivative from a to c of f of x plus the antiderivative from c to b of f of x. And we get the antiderivative from a to b of little f of x. Exactly what was supposed to happen. Now that's accounting for it algebraically and numerically. Let's look at this, let's look at it geometrically also, because it's really going to make a lot of sense if we do this. Okay, let's look at this again. And let's suppose, first of all, just to make things simple, that f of x is non-negative. So the graph of f of x lies above the x-axis. And we'll assume that a is less than b, and that c is somewhere in the middle. The integral of f of x from x equal a to x equals c, isn't that the area between the graph of f of x and the x-axis from x equal a to x equals c? That's exactly what it is. Here the area equals the integral from a to b. I'm sorry, the area equals the integral from a to c of f of x dx. That's what that area is, the integral from x equal a to x equals c. And what about this area right here? The area between the graph of f of x and the x-axis from x equals c to x equals b. Wouldn't that be the integral from x equals c to x equals b of little f of x dx? Sure would. So this area over here is the area from x equals c to x equals b of f of x dx. But what would we get if we combined this area and this area? Wouldn't we get the area from x equal a to x equal b between the graph of f of x and the x-axis? Yeah. And what is that? That whole thing is the integral from x equal a to x equal b of f of x dx. So there we have it. This area, the integral from a to c, plus this area, the integral from c to b, is equal to the whole area, the integral from a to b. Now, some of you might be wondering, Dr. Rossi, is it absolutely necessary that the function here, f of x, is non-negative? No, actually, doesn't matter. F of x can be positive, negative, 0, whatever. Doesn't matter. Okay, well, Dr. Rossi, I hate to be a pain, but here we have c in between a and b. And I know why you did that. It's because here we go from a to c, and here we go from c to b. But does this same integral, does this same equation hold if c isn't in between a and b? And you know what? It does. For simplicity's sake, we put c in between a and b. But it could be the case that c is over here somewhere, greater than b. Or it could be the case that c is over here someplace, less than a. And you know what? This same relationship still holds. If we just assume that C is in between A and B, then it's a lot easier to see the logic. And we say, oh, well, the integral from A to C, that's this area right here. And the integral from C to B, that's this area right here. And oh, if you put these two areas together, you get this area from A to B. Oh, it's a lot more intuitive if we set it up this way, but you know what? C doesn't have to be in between A and B. It still works anyway. So we've seen that numerically. We've seen it geometrically. And that's probably the gem of these proofs that I'm showing right now. We're going to look at the last three also, because we'll need to be well aware of these properties as well. Okay, our next property. Suppose that we take this integral, the integral from A to B of f of x, and we switch the upper and lower limits. What happens? We get the negative of the original integral. Now, I'll show this algebraically, and then we'll go back and see mechanically how it works. And you know, this is where the Riemann sum approach really sheds some light on things. The integral from B to A f of x dx, that we compute the antiderivative, and we take the one that has a constant term of 0, and we evaluate it from x equal b lower limit to x equal a upper limit. And we plug in the upper limit first, f of a, and the lower limit second, f of b. And I think what I'm going to do now is I'm going to factor a negative sign on this. That's going to be negative f of a plus f of b. And now I'm just going to put the positive term first in here. So I'll get f of b minus f of a. And what is this? This is negative what we get if we take the antiderivative of little f of x and evaluate it from x equal a to x equal b. And without the negative sign here, what is this? Isn't that just the integral from x equal a to x equal b of little f of x dx? Negative this thing is equal to negative that thing. Well, where did we start and where did we finish? We started here. We ended up here. And we showed that this thing, the integral from a to b of f of x, I'm sorry, I'm cutting my own throat here. The integral from b to a of f of x dx is negative the integral from a to b of f of x dx. So arithmetically, that's how it works out. Let's look at some Riemann sums and see why this really happens. But remember what a definite integral is? It's the limit of a Riemann sum as delta x, the width of the rectangles, goes to 0. And you know what? As the width of the rectangles goes to 0, we have to have more of those rectangles to fill up the region. So n, the number of those rectangles, goes to infinity. Now, delta x was the width of one of those subintervals. So let's look at it a little bit closer. Yeah, that really is a summation sign. Or excuse for one, but it is. Remember, delta x was the width of one subinterval? And we got our subintervals by taking the interval from a to b and chopping it up into n subintervals of equal length. Well, the length of that interval from a to b was b minus a. And we chopped it up into n subintervals of equal length, delta x. So this delta x was equal to the length of the whole interval, b minus a, divided by n, the number of subintervals. Okay. Now, what would happen if I change or I switch the upper and lower limits? Okay, we get the limit of a Riemann sum. Delta x goes to 0, and at the same time, n, the number of rectangles, goes to infinity. Well, so far so good, no problem. Yeah. And some of you may see what's about to come around the corner here. Some of you may see what's coming. Maybe. Delta x goes to 0 here, I'm sorry. Whoops, delta x goes to 0 here too. My goodness. I'm sabotaging my own proof. Delta x goes to 0, n goes to infinity. And what is delta x? Well, it's the endpoints of the subinterval, a minus b, divided by the number of subintervals. And in that case, this is our delta x. In both cases, f of x is the height of the ith rectangle. And in both cases, our delta x is the width. But you know what? Here, the width of each rectangle is positive. Here, look at this. A is less than b. We're taking a negative length and dividing it by n. We're going to get a width that's negative. See, when we switch the limits of integration around and put the smaller one on top and the larger one on the bottom, we're taking an interval from B to A that has negative length, and we're dividing it up into n subintervals, each one of which has negative length. And what is this whole thing right here? It's the height of the ith rectangle times the width of the ith rectangle. This is f of x sub I delta x, where f of x sub I is the height, delta x is the width. But here, we've got rectangles with positive height, but negative width. So to get this integral, we're adding up a bunch of areas, we're adding up a bunch of rectangles whose areas have negative width. And that's going to make this integral have the negative of the value of this integral. The heights of each integral, the heights are the same. Here, the widths of the rectangles are positive, but oh, if we switch the upper and lower limits here, the widths of each of these rectangles are negative. So when we analyze it that way, when we switch the upper and lower limits, what we're doing is we're adding up rectangles whose widths are negative. So that's why when we switch the upper and lower limits of an integral, we get the negative of the original. Property number 6, if f of x is non-negative and a is less than or equal to b, then the integral from a to b of f of x dx is just the area between the graph of f of x and the x-axis between x equal a and x equal b. So this whole thing is just the area, provided that f of x is non-negative and, of course, a is less than or equal to b. We've been doing area problems for a week or week and a half, so we got this. You know what? I changed number 7 a little bit. In your notes, please go back and change accordingly. If f of x is less than or equal to 0, I'm going to describe what the negative of the integral of f of x is rather than the integral of f of x itself. When I stated property number 7 before, I just talked about this integral from a to b of f of x. But I think it will be a lot easier to talk about what the negative of this integral is going to be. So if f of x is negative, it lies below the x-axis, then the negative of this interval is going to be the area. So the actual geometric area in the positive sense, between the x-axis and the graph of f of x is going to be the negative of this integral. Now, we've done some area problems. This shouldn't be a shock to us. But I think earlier I probably should have opted to state property number 7 this way. So please go back and change things. And just to make sure that I haven't confused the heck out of you, let's look at a quick example, okay? Okay. This example will sort of illustrate the last point. compute the area bounded by the graph of f of x equals cosine of x and the x-axis between x equal pi over 2 and x equal 3 pi over 2. This is an area problem. What is the first thing I always do with an area problem? That's right. I have to graph the bounded region. Okay, at 0, cosine of 0 is 1, and cosine of pi over 2 is 0. Cosine of pi is negative 1, so it comes down here like this. Cosine of 3 pi over 2 is 0. And cosine of 2 pi is the same as cosine of 0, which is 1. We want the area bounded between the graph of cosine of x and the x-axis between x equal pi over 2 and 3 pi over 2. That's this region right here. And property 7 told us what? If f of x is less than or equal to 0, then the area is equal to negative the integral of f of x from a to b. That's x equal pi over 2, x equal 3 pi over 2. Okay. So that means we're going to have negative the integral of cosine of x from pi over 2 to 3 pi over 2. Antiderivative of cosine is what? Sine, right? And so we take the upper limit, 3 pi over 2, minus sine evaluated at the lower limit. And let's see, sine of 3 pi over 2, that's the same as sine of negative pi over 2, which is negative 1. So this is negative, negative 1, minus sine of pi over 2, which is 1. And that gives an area of 2. Okay. Okay, let's do this example. This is a nice one. Sketch the region that corresponds to the definite integral and use a geometric formula to compute the definite integral. Well, let's see. By saying this, I think what they mean is graph the region and compute its area. Okay. So here's our function. F of x equals 1/4 x. Or y equals 1/4 x. Y equals 1/4 x. Isn't that just a line with slope 1/4 and y-intercept 0? So it's going to be a line going through the origin. And it's going to have slope 1/4, which means if we go over 4 units to the right, where x equals 4, it's going to go up 1 unit. Let's see, the rise is 1, the run is 4, change in y is 1, change in x is 4, slope 1/4, yep, that's it. Okay, beautiful. Yep. That's the area of the region that we're computing. The integral is the area of that region because between 0 and 4, the graph is above the x-axis. So this integral is just going to be the area of that rectangle, which is 1/2 the base times the height. And the base here is 4. The height is 1. So it's going to be 1/2 the base times the height. And that's going to give us 2. Okay, let's double check this son of a gun. The integral from 0 to 1, 1/4 x dx is 1/4 x squared over 2. X equals 0 to x equals 1. And that's 1/8 x squared from x equals 0 to x equals 1. Plug in the upper limit. 1/8. Whoops. I'm integrating with respect to x, aren't I? So x goes from 0 to 4. My goodness. What was I thinking? Yes, we're integrating with respect to x. This region goes from 0 to 4 on the x-axis. Okay. So we take the antiderivative and plug in the upper limit. Take the antiderivative, plug in the lower limit. And we get 16 over 8, which is 2. Check. Okay, let's do another one. To do some of the exercises that you're going to have for homework, it's going to be necessary that you know how to do graphs involving circles, semicircles, and so forth and so on. And it turns out the graph of a circle of radius r centered at the origin is given by x squared plus y squared equals r squared. Why is that? Well, let's just take any point on the circumference of the circle. Here is the point xy. And Here's the x-coordinate. Here's the y-coordinate of that point. And now let's draw a radius from the center of the circle to the point. This radius is r. This distance is x. This distance is y. And guess what we got? We have ourselves a right triangle where the hypotenuse is the radius of the circle. The opposite side is the y-coordinate. The length of the adjacent side is the x-coordinate of the point. And just by Pythagorean's theorem, if we take the lengths of the two sides of the right triangle, square them, and add them together, we get the hypotenuse squared. So any point xy that's on the circumference of a circle of radius r centered at the origin has to satisfy this equation. Now let me take this just a little bit farther, because I know that we're probably going to have to do something like this in the homework. Suppose that I have a need to write the equation of this graph in the form of y equals f of x. Y equals something. Well, I take this equation and I move x to the other side, and then I just take the square root of both sides. Actually, what I've done is not quite correct. I have y equals the square root of r squared minus x squared. And this square root, it's a function. You plug one value in, you get one value out, the positive value. So this is going to give us the positive y values on the graph. And where is y positive? Above the x-axis. This equation only gives me the upper semicircle. Suppose I wanted to deal with points on the lower half of this circle. Yeah, I want y equals negative the square root of r squared minus x squared. So first of all, correctly, when I took the square root of both sides, I should have done this, and now that's really correct. That's correct. This thing is exactly the same as that thing. And if I'm dealing with the portion of the circle that lies above the x-axis, where y is positive, then I want the positive square root, or just y equals square root of r squared minus x squared. If I want to refer to the lower semicircle, then I have to do this. I have to write y equals negative square root r squared minus x squared, and that pertains to this half down here. So when I take this equation of the circle, of radius r, and I solve for y equals positive square root will give me the semicircle above the x-axis. Y equals negative square root will give me the semicircle below the x-axis. And in some of our integral problems, like the one we just got done doing, we're going to have to make this observation. Okay, here's our integral. And it says, sketch the region corresponding to the integral. Well, let's see. Our integrand here is of the form r squared minus x squared. So this is a semicircle of radius r lying above the x-axis. And r squared and 9 are the same, so that means that it's a semicircle of radius 3 lying above the x-axis. Okay, I got that. So what we're wanting is, we've got the region corresponding to the integral, I guess. X goes from 0 to 3. Okay, and remember, this is just the top half of the integral. Square root of. Just the top half of the circle from x equals 0 to x equals 3. That's from here to here. So I think we're looking at this region right here. And they tell us, use a geometric formula to evaluate this integral. Okay, I can do that. The integral from 0 to 3 of 9 minus x squared dx. What is this? This is just 1/4 of a circle, right? So that's 1/4 the area of a circle of radius 3. And that's going to be 1/4 pi r squared, or 1/4 pi 3 squared, which equals 9 pi over 4. That's our area. That's the value of this integral. Okay, let's do some that have more of an algebra. Now, we know how to compute these. We know how to compute definite integrals. But let's use the property of definite integrals and the fact that the integral from 2 to 6 of x dx is 16 to compute this, and use the properties of definite integrals to compute that also. So let's see. We want to use this to compute this integral. And by the properties of definite integrals, if you have the integral of a constant times a function, we can bring that constant right out in front. Let me do that again. I want sound effects and a red marker. There, that's wonderful. Bring that constant right out in front. That's one of the properties of definite integrals. So we have -5 times the integral from 2 to 6 of x dx. And we know from what's given that this thing equals 16. And that equals 8. Let's just check. The integral from 2 to 6, -5x dx. Let's say that's going to be -5 halves x squared, or let's say -5 x over 2 from 2 to 6, and that's -5 times, -5x squared over 2, forgive me. So plug in the 6, we get 36 over 2 minus -5 x squared, which is 4, over 2. And got good thing I checked this. -5 times 16, -80, isn't it? Sorry. Okay. So this is 18 times -5. Holy. What is that? 90, maybe? I think so. -90 plus 5 times 2 is 10, which is -80. Oh, thank goodness I didn't mess it up again. Okay, so the check works. And good thing we checked because I left out my negative sign here. Now, this one. This integral doesn't go from 2 to 6 like this one. But there is another property of definite integrals that says the integral from a to a of f of x dx, bottom limit, top limit are the same. That integral is going to be 0. These two things are the same. This son of a gun is going to be 0. Okay, some more exercises. Okay, these are pretty good. Given that the integral from 0 to 3 of f of x dx is 4, and the integral from 3 to 6 of f of x dx is -1, use the properties of definite integrals to compute the following. First one, integral from 0 to 6 of f of x dx. And we have to use these two integrals together. We want our integral to go from 0 to 6. We're given an integral that goes from 0 to 3. And another one that goes from 3 to 6. Are you thinking what I'm thinking? I hope so. Notice that the upper limit of the first is the same as the lower limit of the second. Oh my goodness, let's see. 0 to 3 f of x dx plus 3 to 6 f of x dx. And you know what happens when we do this? And when we add them together, it's like we chop off the top of this one and the bottom of this one, and we take the top half of this and put it on the bottom half of this. We get the integral from 0 to 6 f of x dx. Oh my, tell me it wasn't that easy. Oh, but it is. Integral from 0 to 3 is 4. The integral from 3 to 6 is negative 1. And that gives us 3. The integral from 0 to 6 of f of x dx is equal to 3. Okay, what about the next one? The integral from 6 to 3 of f of x. We have the integral from 3 to 6. The only difference between what we're given up here and what they're asking us to get down here is that they've taken this integral and they've switched the limits down here. So you remember what our property says? If we take this integral and switch the limits, the result is we get the negative of the original. So we're going to get negative 1, which is 1. The integral from 6 to 3 of f of x is equal to 1. Okay, well, I think that covers the properties of definite integrals very nicely. I'll be giving you homework soon.